Hey, welcome everyone. Thanks so much for joining us. My name is Risa Wexler. I am a professor here at Stanford in the physics department and also at SLAC. And I am the director of the Kavli Institute for Particle Astrophysics and Cosmology. We are having a lot of fun all week this week, celebrating our 20th anniversary. It's hard for me to believe that the Institute has been around 20 years now. It was really started to bring together the strength of Stanford and a national lab that's right on our down the road. And it's been a wild ride. I've been here now for 17 years. It's been amazing. I came as an assistant professor. And it's been really fantastic to be part of the real growth of astrophysics at Stanford. From the very beginning of KIPAC, the first director was Roger Blanford and the first deputy director was Steve Kahn. And from the very beginning of KIPAC, this project, which is now called the Vera C. Rubin Observatory, at the time was called LSST, and LSST has now been repurposed. It's still called the Legacy Survey of Space and Time that will happen on the Vera Rubin Observatory. That was a part of our vision for what KIPAC would do from the very, very beginning of the Institute. And it's been one of the core projects that we have been working on now for 20 years. And it is about to come to fruition. The camera that we are building that is currently down the road that Aaron is leading is going to ship to Chile soon and be installed at the Vera Rubin Observatory, and will take an amazing survey of the entire southern sky for 10 years. And it's just going to revolutionize all kinds of areas of astronomy. So we're really, really happy to tell you more about this project and the science that we are really, really excited about doing with it. So thank you for joining us. So this is going to be a panel discussion. We have 5 people here who are all thinking about different aspects of the Vera Rubin Observatory. And Dan Wilkins and I are going to sort of lead the discussion. So let me just introduce Dan and then pass it off to him. Dan Wilkins is a senior member of KIPAC and works on many aspects of black holes, AGN, and galaxy clusters. He is also just a tremendous advocate for talking about science with the public, and has been an amazing person on our team, really getting these monthly public lectures going in a way that really hopefully is engaging to all of you. So thank you, Dan, and I'll pass it off to you.
Okay, thank you, Risa. And it is my great pleasure to introduce our panel of experts tonight. Starting from your left, we have Dr. Yaoyuan Mao, who is an assistant professor of physics and astronomy at the University of Utah. Yao was born and raised in Taipei, and they received their PhD from Stanford, one of KIPAC's own graduate students, in 2016. Before going on to postdoctoral fellowships, first of all at the University of Pittsburgh, and then to Rutgers University in New Jersey, where they received NASA's prestigious Einstein Fellowship. Yao uses astronomical surveys and computer simulations to study astrophysics with a focus on understanding low-mass galaxies and dark matter. And they are an active member and builder of the LSST Dark Energy Science Collaboration. Then we have Dr. Krista Lynn Smith, another KIPAC alumnus. Krista came to KIPAC after completing her PhD at the University of Maryland. She was awarded NASA's Einstein Fellowship that brought her here in 2017. And then in 2020, she moved to Southern Methodist University in Texas, where she was for 3 years before moving on to her current position on the faculty at Texas A&M. And Krista is an expert in the study of supermassive black holes, particularly how the light coming from around supermassive black holes varies and how we can use that to better understand black holes. And Krista has done some really amazing things, repurposing exoplanet experiments to study some of the biggest black holes in our universe. Up next, we have Professor Aaron Rudman, who is a professor of particle physics and astrophysics up the road at the SLAC National Accelerator Laboratory. He did his undergraduate research at Caltech and received a PhD in experimental particle physics from the University of Chicago. He first came to Stanford and SLAC in 1988 to study the asymmetries between matter and antimatter. But after 20 years of wondering what happens to all the antimatter in the universe, he decided to switch to exploring why actually most of our universe isn't made of normal matter or antimatter at all. So since then, he's been studying dark matter and dark energy and played a major role in the construction of the Vera C. Rubin Observatory and is the project lead for the LSST camera that will be installed on that facility. Then finally, we have Kevin Burge here. Kevin is not a KIPAC alumnus, but a future KIPAC member. He's currently a Pappalardo Fellow at MIT, but he will be moving to Stanford next year, where he will take up a faculty position as assistant professor in the physics department. We're delighted to welcome him to Stanford. So before we move on, just a little bit of housekeeping. We have an audience here in the room, and we also have an audience joining us online. So welcome wherever you are joining us from in the world. The format of tonight, we're going to have a little bit of a conversation up here on the stage. And then we will invite all of you to ask your own questions of this audience. Now, those of you online, we will have both a QR code on the screen, and also we will drop a link into the chat on YouTube where you can submit your questions. And then if you see questions that you also think are interesting on there, you can upvote them. And the more votes a question gets, the more likely we are to ask it. And of course, those of you in the room will have the QR code up on the screen as well. So all through the conversation, you can feed your questions and what you want to know about into that. And then once we finish sort of the first part of the conversation, we'll then open the floor to a traditional Q&A towards the end. But without further ado, let's move on with today's talk. And first of all, I would like to invite Aaron to tell us a little bit about the Vera C. Rubin Observatory itself.
Thanks, Dan. So maybe we can go to, I have one slide to show to kind of guide what I want to tell you. So the Vera Rubin Observatory is going to be a unique tool to study the universe. And it's unique because it combines the product of a giant mirror to collect an enormous amount of light from the night sky with an enormous field of view, so that in any individual image, we can see a big swath of the sky. So there are other telescopes that are bigger, and there are other cameras that look at more of the sky, but the product of the two is unprecedented at Rubin Observatory. And so if we look at these pictures, they sort of tell that story. So in the upper left is the primary mirror. That's 25 feet in diameter. And that's the mirror when it came out of the oven at the University of Arizona about 15 years ago. Next, in the middle on the top is the telescope mount. So that's the structure that holds the mirror and holds the camera and swivels around on the sky. Another amazing thing is that it's capable of moving faster than most any other big telescope. And if you want to take pictures of every part of the night sky, moving fast from one place to another is a great feature to have. The next picture in the upper right is the observatory. So the building is done, the dome is almost done, and there you can see it on our mountaintop in Chile. For this sort of astronomy, you want to be in a dark place. You want to be in a high desert. You want to be somewhere where there aren't many clouds. It doesn't rain much. And then the southern Atacama Desert is a perfect spot. Many of the world's telescopes are located in this region of Chile. So then the part that's closer to home is the camera. So that's the instrument that's going to take these spectacular pictures. And I'm honored to be the leader of that project now, and we're building it up at SLAC. So on the bottom left, you see two of our engineers, that's Hannah Pollack and Travis Lang, installing the last part of the focal plane. So we are in the Guinness Book of World Record for the largest focal plane. We have over 3 billion pixels in a region that's 64 centimeters by 64 centimeters. If you ever took apart your phone, the thing that takes the photograph is like this big. It is tiny. So there's nothing else like this out there. In the middle, the bottom is one of our first images. So it's actually a picture of Vera Rubin. This is a famous picture of her measuring galactic spectra. And we thought it was an appropriate way, an appropriate first light image for our camera. And then finally, on the bottom on the right is the camera. So actually the instrument is finished and it's going through its final testing in Slack before we send it to Chile in the next few months. So that combination, collecting a lot of light with a big mirror, seeing a lot of the sky at once, able to take images quickly and analyze them quickly, those are all unique features that are going to enable an enormous amount of science, the kind of science that all of us are really excited to start doing. So.
Perfect. Thank you, Aaron. So up next, I'd like to invite Yao to talk a little bit about their research and what they're most excited about with Rubin.
All right. Thanks, Dan. So I study the nature of dark matter. So the image you see on the left, that is what the universe would look like if you can see dark matter. You can see this filamentary structure that we call cosmic web that is formed as the universe evolved through the gravity interaction of dark matter. Unfortunately, we cannot see dark matter, so this is from a simulation image. So the way that we can study it is by the visible component of the universe, like galaxies and stars. We believe the galaxies are living in this high density region of the dark matter that we call dark matter halos. So in the middle, on the top, you can see kind of a zooming region for a Milky Way size galaxy. You have this gigantic dark matter halo that's around it. For comparison, the Milky Way, this nice spiral galaxy itself, sitting at the very center of dark matter halo. That is, the size is about 10 to 20 times smaller than the dark matter halo itself. Within the halo, you also have some other smaller galaxies that are orbiting around this, cloud of dark matter. Those smaller galaxies have a mass that's much, much smaller than the Milky Way, this spiral galaxy itself. You can barely make out that tiny galaxy on the lower right there. But these galaxies are particularly interesting because they are very rich in their dark matter counterpart. And by finding this very, very tiny galaxy, we can kind of get a peek of the nature of dark matter and how that evolved with time. So if you go to the next slide, the two challenges we have in using these tiny galaxies to study dark matter, one is observational. So on the top of this slide, I'm trying to say that if you are trying to find this very, very faint galaxy, you can only find them in a very nearby universe. That is not because they only exist in nearby universe. In fact, they also exist in very far universe, but they look so dim if they are far away. So in order to study that, you need to find those nearby ones. But the nearby universe is much smaller compared to your background universe. So then you have a much smaller volume that you can find those things. So it's more and more difficult to find them. But beyond observation, there is also theoretical challenges that we are facing to study these galaxies. So we need to understanding whether the galaxy formation itself is connected in some way to how the nature of dark matter that impacts this formation of this tiny galaxy. So you can see these two pictures on the lower left showing you different theoretical models for dark matter and then produce different kind of structure. So we are distinguishing this kind of structure by counting the drop of these little galaxies in the universe to study the nature of dark matter. And Vera Rubin Observatory is going to give us a data set that we will hopefully using that to tell us something about the mystery of dark matter.
Thank you, Yao. Krista, why don't you tell us a little something about black holes?
Okay, yeah, great. So what I study is the physics of supermassive black holes. Oh, thank you. And how they kind of devastate the evolution of the galaxies in which they live. So this is a picture of a barred spiral galaxy. It has that bar in the middle with the spiral arms. And this is the type of galaxy we think the Milky Way, our own galaxy, most resembles. And deep in the center of all major galaxies, including our own, is a black hole with a mass of millions to billions of times the mass of the sun. Now, most of the time, those black holes are quiescent. They're minding their own business. Nothing has stumbled close enough to tumble in. But about 10% of the time, these black holes are actively feeding and consuming huge amounts of material and releasing a huge amount of energy into that galaxy. So when that happens, we have a situation like the one pictured here, where the black hole is at the center and a ton of material is swirling into it like water down a bathtub drain. And there are multiple components to the image that you're seeing here, including the accretion disk, the material that's falling in, this jet that's being ejected by the magnetic energy of the black hole, and then this cloud-like torus structure that surrounds it. And in order to fully understand the physics of this object, we have to use the entirety of the electromagnetic spectrum, which is different energies and different types of light, because each of the pieces of this puzzle emits in a different regime of that spectrum. And we need to use different types of telescopes to make that study. So all of the telescopes pictured above in those different parts of the electromagnetic spectrum are telescopes that I use in my research to study all those different pieces and integrate those together to understand the relationships and the causality between all those different regions. So some of the things that I study, there's a few. One of them is the behavior of the material as it falls in itself. And that material is magnetic, it is dynamic, it is turbulent, and so it varies with time. And on the right are some what we call light curves. Those are plots of how bright something is over time. And we can do a lot of amazing physics with the details of those light curves, what's happening in that accretion material with the magnetic fields inside the jet, and how all those different things affect each other. Additionally, I study binary supermassive black holes. So we have beautiful pictures from Hubble and other telescopes that show that mergers between galaxies happen all the time. And if that is true, and they all have supermassive black holes in them, then naturally we would expect there to be binary supermassive black holes. And then finally, that central engine, as we call it, of the accreting black hole doesn't exist in isolation. It lives in that galaxy, and it releases vast energy across the galaxy that can really terminate, or even in some cases trigger waves of star formation that affect the evolution of the galaxy. And it turns out that in order to explain the diversity of galaxy colors and shapes and sizes that you see in these beautiful images, that kind of interaction between the central engine and the host galaxy is absolutely required. So those are the kinds of things that I'm looking forward to looking into the next 20 years. But especially this timing interaction, the Rubin Observatory is going to be foundational in helping us open that up.
Thank you, Krista. Now, Kevin's research, or part of it at least, is all about gravitational wave sources. So these are ripples in the fabric of space itself. And Kevin is interested in where gravitational waves might come from within our own galaxy and how we can find them with the Vera Rubin Observatory. So once we've got the slides back, I can see Zinan's working on it. I'll hand over to Kevin.
Yeah. So many of you may have heard of gravitational waves. So recently, in just the last 10 years, actually, we detected them. In 2016, I believe, was the first detection by the LIGO detectors. And so the ones we detected came from merging black holes. And so you get gravitational waves when you take two really dense things and merge them together. And it was an amazing result because Einstein's theory of general relativity predicted that these should exist over 100 years ago, and it was a huge achievement to see them. What I study are gravitational waves that come from things in our own galaxy. Yeah, so this really gets me excited for the following reason. So the gravitational waves we're seeing right now are coming from very far away. It's taking billions of years for them to get here to Earth. That's how far away they are. But it turns out that there are actually a lot of things in our own backyard, the Milky Way, that are emitting gravitational waves that we can't see yet because we haven't built a detector to be sensitive to them. But we're actually working on it by putting one up in space. Now let's see. Okay, so the gravitational waves in our own galaxy actually are not coming from merging black holes. They're coming from merging white dwarfs. And I know everyone here may have not heard of what a white dwarf is, so I just want to give a brief recap. So most stars at the end of their lives leave behind these things called white dwarfs, and you can see a picture of them there on the left. And basically, the way to think of a white dwarf is it's the leftover core of a star. And to give you an idea of how dense these things are, they're about the size of the Earth, but they weigh as much as the sun. The sun weighs 1 million times more than the Earth, and it means the matter in them is 1 million times more dense than what we're used to. A teaspoon of matter from a white dwarf would weigh as much as an elephant. And what I do is I go looking for these things orbiting each other with orbital periods of just a few minutes, basically whipping around each other, going thousands of miles per second. That's how quickly they're moving. And so the cool thing is you don't actually need gravitational waves to find them. So you heard the word light curve mentioned earlier. If you look at the light curves of these objects, basically how bright they are over time, what you can see are dips in brightness that happen when one of them passes in front of the other. The same way when planets pass in front of stars, we can infer that they're there from those dips. It's just here the dips can get really big because the white dwarfs are so similar in size, unlike a planet, which is much smaller than the star it goes in front of. And so this is just a theoretical movie showing what the light curve would look like there in the upper left. Let me show you some real data of what it looks like when you take a movie of the sky of these things. And this is very similar to the type of data the Vera Rubin Observatory is going to be taking. Oh, that didn't play the movie. There we go. So if you look on the left, in the lower left corner, you'll see a little star that repeatedly disappears. This is real data, by the way. I took this movie on a telescope. So this is a pair of white dwarfs that's disappearing every 6.91 minutes as one passes in front of the other. And on the right there is what you were seeing was the light curve. Yeah, their movie's continuing. So anyway, this movie was taken with a high-speed camera just staring continuously. But the beautiful thing is you don't actually need to stare at it with a high-speed camera to find it. You can actually play tricks with algorithms and computers to take data where you take a picture once every few days to find this pattern. And so that's what I'm really excited about finding with the Vera Rubin Observatory.
Okay, so this was amazing to have this introduction to all of your research. One of the things that I think is so incredible about the Vera Rubin Observatory is the range of science that it can achieve. I mean, we heard about dark matter and small galaxies, which you need either resolved stars or very low surface brightness features. We heard about different kinds of time series data to look at black holes and white dwarfs, very, very different scales from, things smaller than the sun to way more massive. Aaron, you didn't even talk about weak gravitational lensing or how we learn about dark energy with this survey. Aaron, I wonder if you could speak to how did you think about, how did the team think about designing an instrument that could really achieve this broad range of science cases?
Thanks, Risa. So actually, let me preface it by adding a little bit, and it directly talks to that point. How can we do so much science with this new telescope and this new instrument? One of the keys is that we're going to take images in a survey mode. So most telescopes, scientists would make a proposal and say, I want to look at this object or this region of the sky, be granted some telescope time, and go take those observations. We're not going to do that. We are conducting an all-sky survey. So the telescope and the camera have been designed so that in a few nights, we can get at least one image of every part of the available night sky from our mountaintop in Chile. And we will do that every night for 10 years. Well, Sometimes it's going to rain, there might be clouds, things might break. Okay, as much as we can, we're going to take images every night. At the end of 10 years, we will have over 825, well, that's what we've signed on the dotted line, that will deliver 825 images in every direction of the sky. And we're going to use those images in two different ways. In the first way, we'll combine the images together via our computer algorithms. And so if you're looking for dim objects, like Yao described, you want to look at the combination. That will let you look for unbelievably dim objects in a way that it really gets after them better than other telescopes can, because we're combining different images, and little problems that might be present in this image or that image will tend to cancel out. The other way that we'll use the images, and that gets to the other science you heard about, is for every image we take, the data will come here to Stanford. It will go to a computer center at SLAC and be analyzed in just a minute or two and compared against previous images in that part of the sky. Anything that changes will get flagged, and a message will go out to the whole science community: in this direction, this thing has changed. So that is really a unique combination as well. Now, in terms of figuring out how to build it, there are a number of unique features. One is that the telescope is made out of 3 mirrors. So a common choice is 2 mirrors. The Hubble Space Telescope is 2 mirrors. Most telescopes are 2 mirrors. We have a third, and the reason we have 3 is because that helps us look across a big swath of the sky at once and get good images. And in every image, the size of our images is 7 times the diameter of the full moon. By comparison, a telescope like Hubble or the giant Keck telescopes in Hawaii or the new James Webb, they look at a tiny piece of the sky, a fraction of a degree at once. And so if you want to look at the whole sky, that's what you would design. For us in the camera, the challenge was to build such a big focal plane. And that involved lots of intricate decisions about how to put things together so that you could successfully have this very tightly packed focal plane that was enormous. Now, I'll just mention one challenge. We wanted to use the area in our focal plane at maximum efficiency. We didn't want gaps between our image sensors. We didn't want regions where you don't get any image. That was difficult. One of my colleagues always likened it to parking a Maserati in between 2 other Maseratis with only a centimeter between them and not having anything scratch. So that's the kind of challenge we faced. We have been successful in that, and we're definitely looking forward to having all the pieces together and to start this fantastic survey.
Cool. So if I can ask a follow-up to that then. So each part of this camera, how does the price of one of these bits compare to the Maserati?
So we have 201 individual sensors. They're kind of the cousin of the thing in your cell phone. So we use something called the charge couple device, and your cell phone is a CMOS imager. They're pretty similar. Each one is 4 centimeters by 4 centimeters and 16 megapixels. They were built custom for us, and they each one costs about what a Maserati costs, actually.
So don't drop them.
Definitely not.
I wonder if I could ask Krista and Kevin about kind of making sense of this time domain data and how you're thinking about that. There's been a whole community process to balance different science cases and what kinds of different data, you need for black holes or white dwarfs or whatever supernovae. And how have you thought about that for your own science? And then how are you thinking about actually analyzing those data?
So I'll go first. So I had the privilege earlier today of learning more about Kevin's research. It really brought home to me something that's been true, that's been more and more clear to me over the past decade, which is that the way that you use these fantastic instruments that people like Aaron are building, it depends very sensitively on the type of science that you want to do. And so, you build an instrument with fantastic capability, and then there are battles between communities that want to use those capabilities in very different ways. So Dan mentioned in the introduction that I use exoplanet hunting satellites to do this accretion disk black hole physics. And one of the reasons I like those satellites is because they take pictures of the sky at exactly the same interval for many, many months to years. And that really helps because if you remember the light curves I showed you, those light curves were kind of random looking. They went up, they went down, they stayed down for a while, they flare, they go quiet. And there's a lot of physics in that. But there's a lot of other things that telescope does. It sees a little bit more of the sun. It sees a little bit more of the moon. It gets hotter and it gets colder. The way the light is processed changes with time. And those systematics, as we call them, can obscure the signal. And it turns out that that very regular sampling, the way we analyze those data, that makes it a lot easier to tell the systematics from the signal and to analyze the signal itself. But that is very different from the kind of science that Kevin does. So
yeah, so I can talk a little bit about how I am going to approach analyzing the data. I have a lot of practice with other cameras that have been looking at the sky. So I'm trying to look for things that have repeating patterns in them every few minutes in images that are taken days apart. That's actually pretty hard to do. But it turns out that there's a piece of computer hardware that many of you may know called a GPU. It's a graphics processing unit that is amazingly good at this problem. So GPUs were originally invented to run video games, basically render images very, very quickly and send them to your monitors. Turns out they're actually really good at taking in things like images or large arrays and crunching numbers and spitting out interesting results. And so what I do for a living is basically take all these light curves, feed them into GPUs, draw many kilowatts of power while doing it, and then get out amazing discoveries that I then follow up with other telescopes. But to me, it would be impossible to do the science that I do with Rubin if it weren't for that technology. You'd never be able to do it with CPU-based algorithms.
And so when we're talking about these light curves and we're looking at how the brightness of the light we're seeing is varying over time from these different astrophysical systems. So I guess, Kevin, you're looking at these white dwarfs going around each other. We can kind of understand this variation in terms of this motion. But Krista, what are we looking at around a black hole? What are these light curves telling us, and what part of that system are we looking at?
Yeah, so that depends on the color that you're looking in. But if we're talking about the optical emission, which is the band of the electromagnetic spectrum that Rubin will be observing, we're mainly looking at different pieces of that disk of material that's swirling into the black hole. So the regions that are closer to the black hole are hotter, and so they are bluer. Hotter things give off bluer emission, shorter wavelength, higher energy light. And as you move outward through the accretion disk away from the hole, you get to cooler and redder wavelengths of light. And the wave bands, as we call them, the regions of visible light, that's light you can see with your eyes that Rubin will probe, very nicely samples the different regions of that accretion disk as you move outward. So for example, we don't know whether something happening very close to the black hole in the X-ray, very hot region that Dan studies very often, which we call the corona, if something happens there, a flare or something falls into the black hole, gets very hot, there's a flare, and that emission then kind of reflects and propagates and moves outward. Or if something comes into the outer regions of the accretion disk and there's fluctuations that occur because of all kinds of turbulence, then they move inward. So how do we know if we have a camera like Rubin's, which is taking images in all of those colors at the same time, then we see a flare in the red band, and then we see it in the orange band, and then yellow, and then green, and then blue? Well, we know that it's moving from the outside in. And so that's just one example of how we can understand how these things propagate. And in the end, kind of the end game is that we're studying how space-time is bent in the presence of that black hole, because all that material the shape of that bathtub drain is driven by strong gravity and then the curvature of space because of the hole. So that's the ultimate kind of physics, but understanding how those pieces of that central engine are related is going to be key, and Rubin will speak to that.
Cool. So I guess by tracing all these different colors of light and how the brightness is changing as a function of time and how things move from different colors, we're kind of turning the snapshot pictures that we're used to seeing from telescopes into a movie, really, just following material as it's going into those black holes and seeing exactly what's happening to it as it meets its final demise, I guess.
Yes.
Let me switch gears a little bit and ask you, Yao. I know you're interested in how we're going to learn about dark matter with galaxies and the new ways we'll be able to study galaxies with this observatory. Can you tell us a little bit about what new ways we'll be able to learn about dark matter? It's kind of confusing how we can learn about dark matter from light.
Yeah. So well, I wouldn't say it's a new way, but like Aaron just mentioned, like Rubin is going to find like the faintest, the smallest galaxy that we ever know today. Many of you might have heard of the JWST Space Telescope. The telescope is like looking, on the other hand, in the very, very distant universe, also trying to find one of the very early galaxies that is formed in a very, very early universe. Now, that requires you finding, because the field of view of JWST is such a small field of view, so you kind of need to have some idea about where you are looking for in order to find this very rare galaxy. Now, Rubin is going to change this completely. We will be able to find this tiny galaxy in our nearby universe because Rubin covers such a wide range of the sky. And so really one of the big challenges, how do we identify this? We have a too much data problem in a way. Rubin is going to find faint object that is in the distant universe that is going to confuse us with the tiny object that we are trying to find in the nearby universe. Finding a way to distinguish these objects is kind of the main challenge we are facing. Now, coming back to your question, what do we do once we find these faintest galaxies that we have ever known? So these galaxies, their existence itself tell us something about dark matter, because different theories predicts the dark matter can form different kind of dark matter halo that I mentioned earlier. And if we believe all the galaxies live inside this kind of dark matter halo, the existence of some of these tiniest galaxies tell us what kind of dark matter halo there must be so that we can host these small galaxies. And that would tell us what kind of dark matter may not be true because they will not be able to form these very, very tiny dark matter halos. So even the existence of finding these objects will actually tell us something about dark matter.
That's great.
So I wonder, Yao, how do the tiny galaxies and what they tell us about dark matter relate to and interact with what we might expect from studying the bigger galaxies in our universe?
Yeah, so I talk about tiny galaxies just because that is kind of my research area. But one really cool thing about Rubin is that, you know, as we already hear, like it can enable so much different sciences by just doing a survey. And actually a bunch of people who are interested in dark matter come together and we kind of say, well, what are the different ways that we can do to study dark matter with Rubin? And I think we come up with a 200-page paper with maybe 35 different ways to do that, ranging from even like white dwarf luminosity function to galaxy clusters. And they all have like different ways that we can understand dark matter. But just as an example, one way you can study dark matter through like huge galaxy clusters is by looking at the distribution of a galaxy when there's merging events. So Rubin is going to find detailed images of these galaxy clusters and also how they may have interact with each other when there's merging galaxy cluster. And you can even measure the wobbling of this galaxies inside galaxy cluster. And that will put constraint, like put limitation on how strongly dark matter particle can interact with each other, and hence tell us something about the nature of dark matter.
So we heard Yao talk about dark matter. I know we're also really interested in dark energy and what it's doing to the universe. Aaron, can you tell us something about how this observatory is going to contribute to that?
Yeah, absolutely. And that's my own scientific interests are really focused on the other dark thing, which we call dark energy. That's just the name we give to the thing in the universe that is causing the expansion of the universe to accelerate. And that was discovered about 25 years ago. But its ultimate, the ultimate cause of it, or what dark energy is actually not known. There's some solid ideas, different possibilities. The data is pointing in one direction, but really our measurements are not that accurate. So, one of the interesting things about dark energy is if you are curious to know or curious to understand what will happen to our universe into the distant future, you need to understand dark energy. What is the fate of our universe billions of years from now? It's incredible that we can even ask such a question and get a coherent answer, but it depends on the nature of dark energy. It's also, for me, it's also connected to the particle physicist in me, because, it's not a particle, but is it a field? Is it a quantum field of some sort? Which it sort of should be, is one of the big questions. So we're going to study it in multiple different ways. And one of the advantages of Rubin is we can bring to bear many different techniques using galaxies, using clusters of galaxies, using supernova to study it. And maybe I'll mention one way that I'm really interested in to study dark energy. And it really gets at the expansion, measuring the expansion, is using these rare systems where you have two galaxies lined up, one maybe just a few billion light years away, and the other, 8 billion light years away. And sometimes you get lucky and they're really lined up well, and then you see something spectacular. You will see multiple images of the distant galaxy because its light is bent by the gravity of the galaxy that's closer. So the jargon is strong gravitational lenses. Sometimes you get something called an Einstein ring. These are rare objects, and they're dim. They have these unique shapes, and Rubin is going to find lots of them. So we're going to be the finder. We'll find them. And the other thing we'll do, and this connects to what Krista talked about, they sometimes one of the galaxies, usually the distant one, changes its brightness over time because it's got a black hole in the middle that's acting up. And you see multiple images, and the changes happen at different times in the different multiple images because the path the light is taking is different. It's got a different distance. And you can use that fantastic feature to learn about the expansion of the universe. So I'm really excited about that. People have been doing that. I have done analysis of these systems with one or two. Sometimes a student can get a whole PhD thesis on one such object. We think we'll see hundreds. So that's the potential we have.
Fantastic. And I have to say that's one of my favorite little tricks our universe has, is this gravitational lensing, because not only, as you say, can we measure how space and time themselves are curving, and we can measure the expansion of the universe, but we can also take what we think is a big telescope like the Vera C Rubin Observatory or the James Webb Space Telescope, and we can turn them into an even bigger telescope because these things act like giant cosmic magnifying glasses. And one of my favorite things is to look at black holes on the far side of the universe when we can magnify them. So I guess at this point, Risa and I have been grilling this fantastic panel for a while. We should probably take some questions from our audience. So anyone in the room who has a question, please raise your hand. And I'll get us started actually with a question from online to Kevin. So you were talking about gravitational waves from within the Milky Way, and that piqued the interest of our audience. And they were interested in what this new sensitive instrument is and how it works that can detect gravitational waves from the Milky Way.
Okay, so the actual gravitational wave detector is called LISA. It's the Laser Space Interferometer Antenna. It's actually being built mainly by the European Space Agency, but in partnership with NASA. In a nutshell, for those of you who know LIGO, LIGO is what we call an interferometer. It kind of has this laser beam that it shines down to a reflective surface that comes back, and it shines it down another 4-kilometer arm, and it does something called interfere these lasers to look for tiny changes in the lengths of the arms, and that's how it detects gravitational waves. What LISA is that in space, basically. So it's 3 satellites, and each have 2 laser beams coming out of them, shining to the other 2 satellites. And so they form this triangle, except these things, the distances are much bigger than 4 kilometers between them. We're talking about like 1,000,000-kilometer scale distances. And so they're measuring with the lasers that they bounce between them, tiny changes in the distance between the satellites. And the idea is when a gravitational wave passes between the satellite constellation, that causes them to wobble. And we're looking for the wobble from that. The reason you can't do that on Earth is it's fine to look for what we call high frequency gravitational waves on Earth. So things that happen very quickly, like 100 times a second. But if you try to go to low frequency, so things that are happening every few minutes, the seismic activity of the Earth prevents you from doing that. The Earth is vibrating, we know that. And so unfortunately, we can't do it from the ground, and that's where space comes in. So this should launch in about 10 years. They've already sent up what we call a Pathfinder mission. So they've demonstrated a lot of the technology in space already, and they're working on building the satellites right now. And basically what I'm doing is getting ready for that and finding all the things that they're going to see when they turn on.
So you're going to find these things with the Vera C. Rubin Observatory before LISA is able to do that. Will LISA find the same things, like
so
just later in time?
Basically, yeah, when LISA turns on, I'm going to tell them, look there, you better see something with a 7-minute period. And if you don't, your detector's not working. So yeah, we're actually going to use these to calibrate their detector and tell them whether they're seeing what they should, which is kind of a cool inversion, because right now with LIGO, when we have merging neutron stars, LIGO tells us, oh, we think there should be some light from that, and every telescope in the world wants to go find it. I'm turning that on its head and telling the gravitational wave detector, basically, there better be something here. That being said, LISA's going to find a lot that we can't see yet. But the cool thing is even the ones that we weren't able to find by searching the Rubin data, some of them are going to be tricky signals to pick up blindly. But when LISA turns on, it'll say, hey, there's something here, and it has this period. And then we can actually look back at all of these photographs that Rubin's taken over the last 15 years before that and go, oh yeah, the signal was there. We should have looked harder, I guess, at this one.
Okay, do we have any questions from the room? Yes. So the question was, what is the spectral response of the telescope and how do you measure it?
So I'll take that. So we see light from a little bit into the ultraviolet to the near infrared. So if you're calibrated in wavelengths, 350 nanometers to about 1,000. So that includes the visible band. When we take our images, we take them with a filter, and each filter is designed to see a piece of that spectrum. So we have 6 different filters, each covering roughly a sixth of those wavelengths, and we alternate. It depends a little on the time of the month, whether the moon is up or not, which filters you want to use. And we try in a given night. In a given night, we would switch filters maybe 10 times as well. But we don't have any more spectral information than that. And that is obviously that's valuable information if you have a real spectra. And there are some other big projects that are measuring spectra for tens of millions of galaxies. And some of us are thinking about how to get up to hundreds of millions of spectra as well in the future.
Great, thank you, Aaron. Okay, yes, at the front. So the question was, is anything about Rubin's imaging and its program adaptive, and can it be adapted based on what it sees or what it doesn't see?
So So there's two aspects to that. There's one way in which we adjust our images. We have a system, it's called an active optics system. And we take images out of focus in the four corners of the focal plane. And out of focus stars are very useful to see whether your telescope is in focus, and whether it's aligned, and whether the mirrors have the right shape. And once every half a minute, we'll adjust all of those to try to get the very best images. And if any of you are amateur astronomers, the test there for amateurs is called the STAR test. And we use the same, that's used in professional telescopes as well. In terms of where we take images and how we take them, for the outset, we're actually not going to do that differently depending on what we see. The only exception is we will devote a couple % of our time for specialty images. So Kevin mentioned, gravitational wave events that might be neutron star in spirals. So finding more of those, only one is known, finding more of those would be super exciting. We are well placed to do it because of our giant field of view and because we can move across the sky so quickly. So we haven't decided for sure, but we'll probably spend a few % of our time getting a message from LIGO or from a neutrino observatory in Antarctica called IceCube that says, we see something interesting in this direction. We'll slew over, take a couple images, and then continue on our day, or night. But we will do that, I think.
Okay, another question we had online, and I guess always a question when we're building a big new facility like this, is how does it compare with kind of the big famous facilities that people have heard of, like the Hubble Space Telescope, the James Webb Space Telescope? And I guess you touched on this a bit at the beginning, Aaron, when you said that what Rubin is going to do is survey the sky. It's just going to scan the sky night after night, whereas James Webb and Hubble work much more like pointed observatories. You choose something to look at, then you go and stare at it, and we've explored tonight just the power of doing that in different ways. But I wonder if the panel have any thoughts on actually how do we get these observatories to work together when Rubin discovers something, or when we're making a movie of stuff falling into a black hole using data from Rubin. What do we need to do with the other facilities to piece all of this information together in a useful way?
I can start that all. I'm sure my fellow panelists have things to say. So there are lots of telescopes actually that do this kind of survey maneuver. There have been some in the past that have done surveys that had so many colors that we call them spectra, like we can see very detailed features in how the colors behave. We also have survey instruments in X-ray and in the infrared, in the radio, upcoming. So there are, in all those pieces of the spectrum, there are survey instruments. And then there are the big, what we call the big glass, the instruments that you point to take detailed observations. And at least in the case of these black holes, it's important to kind of look at a survey instrument like Rubin and plan how, an upcoming X-ray survey, or propose your own X-ray survey experiment to monitor the sources that Rubin will be seeing at the same time in the X-ray or the radio, to see how the jet or that coronal plasma right over the black hole responds to the disk. But in terms of how the big, traditional telescopes like Hubble and Webb and Keck come into play, in order to fully understand, these relationships I've talked about, you need to know a few things like the mass of the hole, or the rate at which material is falling in. And it turns out that in order to get that information, you need a very detailed spectrum, which is light that passes through a slit or a prism and is reflected outward. And these big telescopes can do that one object at a time. And you need to look for a long time, for like 20 minutes, to get a good enough spectrum at one object. So you need to use these traditional facilities to get sort of the ancillary data, the extra information, to interpret the time domain data in a more consistent way.
Great. And
I might even chime in on that one for a minute. I mean, I think one of the cool things in astronomy, and one of the things that we're really excited about in the next decade, is the complementarity between the different kinds of observatories that are coming online, right? So JWST is just finding absolutely amazing things, very deep in the universe, but it's a tiny, tiny, tiny fraction of the sky. So it won't be able to survey the entire sky. Rubin will be able to find all kinds of interesting things. And then we are going to want to follow them up with, if they're very interesting, with everything we can get our hands on. So even in the case of the strong gravitational lenses that Aaron talked about, Rubin will find a lot of these. And then we will want to have space-based data to get even higher precision information, but we'll want to know where to point. And there are many examples where we want either different resolution, more information as a function of wavelength, or things in different wavelengths or in different time series.
I think one challenging that we have been facing is how do you go from that vast imaging to the resources that we can follow with is very limited, either with space telescope or if we want to follow up with the ground-based telescope that has like larger mirrors. So like I think one thing that the scientists we have been trying to do right now is kind of finding a systematic way that we can, once we get the Rubin data, how do we filter the interesting thing? And this is really a difficult thing because there are going to be things that we never expected. And we couldn't really develop algorithms and I say, well, this would be the criteria you just follow with all these things because there's going to be things that we never thought about.
Yeah, I just wanted to add to that. So something that's special about telescopes like James Webb and Hubble is we would love to, as astronomers, to just build many of them and put them up, but they're expensive. And you have to have a pretty good reason to justify, hey, we need to spend this many billions of dollars to build James Webb. And that's driven by science, our discoveries. And what I think is exciting about Rubin is Rubin's going to give us all these new discoveries we didn't expect. And the next James Webb or Hubble is going to be driven by those discoveries. We're going to say, we need to build this new type of telescope because we know these things exist now, and we have no way of getting that special kind of data that we now understand we really need to get. And so I think that's going to be one of Rubin's biggest legacies, is it's really going to drive the next class of astronomical observatories at all wavelengths.
Cool. Changing gears a little bit, just as we come up to the end, just a couple more questions that came up online. So a lot of people are hearing about concerns about thousands and thousands of small satellites that are being launched now, particularly by SpaceX for things like Starlink internet. Is that a worry for Rubin? Is that going to affect the science Rubin can do? Is it something that Rubin will have to work around?
So yeah, we've been evaluating that carefully. Those satellite constellations will make a streak across our images. They will affect significant, if the full constellations are built, it will affect a significant number of images early in the evening and late in the evening. That said, we estimate that it will just be a nuisance. Whether it's a minor nuisance or a bigger nuisance, we'll see. But we can, obviously those streaks are easy to find. We'll sort of blot them out and ignore anything that's in them or nearby. And the fraction of pixels we'd lose is small. It's a few percent in total. Yeah, there's some potential that it might be worse than that, depending on what else is built. There has been some work with Starlink to get them to improve or to lessen the reflectivity of the satellites, and they've improved a little bit.
Okay. And then I guess on a slightly lighter note, I guess to finish, and this is a question for all of the panel from online. So as a high school or college student listening to this, hearing about the Vera C Rubin Observatory and all the amazing science that we're hoping to do with it, how can someone figure out the promising research topics to work on in the future? What would your advice be?
So I'll try, and I'm the oldest person up here. So it's not easy to figure out what is going to be the most exciting thing, in the future, right? The future is tough. But one advice that people, professors commonly give their students is to not follow the crowd. Because if everyone is working on some topic, that means everyone already knows it's exciting. And what you might try to do is to think about something that everyone isn't doing. Now, it's hard. Often people, if you manage to do that one time in your career, you're doing well. But that's something to think about. And that applies kind of at the detailed level and, a little bit in terms of, are you interested in astrophysics and cosmology or in particle physics or condensed matter physics or, chemistry or something else? But that's as close as I could come.
Yeah, my wisdom from my research is kind of the following. People are impatient and not a lot of people want to work on things like Rubin that take 10 or 20 years to get to. And if you're young, it's usually not advisable to bank your career on something that far ahead because you need to get papers out. But if you can look at what's coming in the next 10 or 20 years and come up with clever ways to kind of address some of the problems that are going to be addressed by those data sets 10 or 20 years ahead of time, you're really positioning yourself well to take advantage of those big data sets and be a big player in them when they finally come to fruition. So that's sort of my tip along those lines of something to look out for.
I will just say that one of the things that to me is so exciting about the data from the Rubin Observatory is that it's going to be public. We are expecting about 10,000 scientific users. There will be yearly data releases of all of the data to those users and nightly releases to the entire astronomical community about the million things that changed in the sky. And there will be data available to the general public. And along with building the observatory, scientists have been working on building essentially accessibility to the data. So I'm really, really excited about the promise of these data to really engage even high school students in learning how we think about astronomy and what some of the key questions are.
Excellent. Well, on that note, it looks like we are out of time, unfortunately, but I think this has been, I've certainly had a lot of fun up here with this fantastic panel. So let's give them a big round of applause. And just before we finish, I would like to hand over to Zinandu, our Outreach and Engagement Manager, who would like to tell you a little bit about upcoming events we have.
Great. Hi, everyone. I certainly wasn't expecting to be called, but I would be more than happy to walk you through with our upcoming events, which Dan is currently pulling up. Well, while we're waiting for the slide, so a couple of very exciting things. First, we are going to have a solar eclipse viewing party here at Stanford. That's in about a month on October 14th. Well, fingers crossed that we're going to have a clear sky. Otherwise, we can't really see anything. And in the meantime, if you're interested in engaging with KIPAC members and scientists a little bit more, we're going to be participating in the College of San Mateo Family Science Day with a hands-on activity. And of course, feel free to bring your friends and family. There's going to be lots of planetarium shows and also demonstrations. And finally, our KIPAC professor, Susan Clark, will be giving a talk, public lecture, on cosmic magnetism at the Cal Academy on October 2nd. So I believe that Risa also gave one just not long ago. So it's going to be a fantastic experience. You'll get to hear the lecture in a planetarium. So if you want to get tickets, I will also email this whole slide to all of you after this event. And finally, if you want to keep following us, there's our social media channels. And of course, I would assume that some of you are also on our mailing list. But if not, this is your chance to also stay connected with us. So thank you very much for giving this opportunity.
All right, just want to say thank you to everyone for coming. It was great to have you, and we're really excited in the next few years to actually share what we really discover from this incredible observatory. Thank you.